So let's go back to our Reese's Pieces example. We'll look at this example a little bit more, and then we'll move on to some other examples. But again, let's say we're given a bag or a sample of 50 candies. So sample size here, or N, is 50. And we want to determine the proportion of candies that are orange. So let's imagine that out of our sample of 50, exactly 20 are orange. So our sample proportion then would be P hat equals 20 over 50, or 0.4. So remember, a proportion would be a number between 0 or 1, or 0 and 1. And so if we're asking you for a proportion, you would take the number that fall within a certain category and divide by the total number. So here we're taking the number of orange and we're dividing that by the total number of candies. This is important just because I want you to pay attention now to whether questions ask you for probabilities or proportions or percentages, because we'll expect you to be sharing your answers in particular formats. So be really careful in terms of thinking about what you're being asked for. Okay, so the idea now is that, again, we just have our one sample, but we need to imagine, what if we repeated this process many times? What if we took many samples of size 50 from the population, and each time we figured out a sample proportion? We did this over and over again, and then we collected all those sample proportions and graphed those proportions. What would our distribution of proportions look like? To help you visualize this, I wanted to bring up a special applet so you can actually see this in action. So let me just quickly escape here and go to the applet. So here's what it looks like. So we have a nice little candy machine here, and this is our population. So these are all the Reese's Pieces that have ever been made. And we want to take a sample of size 50. So I've set things up so that we're going to take 50 candies. In the population, let's say that the probability of getting an orange candy is 0.5. Let's say in the population, 50% of the candies are actually orange. So I'm sampling from a population where 50% of the candies are truly orange. I'm just going to draw my samples. I'm going to keep the animation here just because I think it's kind of fun to watch all the candy come out of the candy machine. But notice what's happening. We took all this candy out and we're looking at the proportion out of 50 that are orange. So in this case, P hat is 0.58. Earlier we had P hat of 0.4. So let's turn off the animation and we'll just do this a few more times. I did it again. Now this other sample has a P hat of 0.52. Let's do it again. 0.5. Let's do it again. 0.62. Hopefully you're getting the idea here that we're changing it a little, or each time we're taking a new random sample and each time our sample proportion might be a little bit different. And hopefully you're seeing below, down here, underneath the candy machine, that each time we have our sample proportion, we're plotting it. We're creating a distribution of our sample proportions. So let's say I took lots and lots of samples. I'm going to change this to 100. So we're going to take 100 more samples. Each time the sample is size 50, and each time we are looking at the sample proportion. So you can see what would happen. So again, over time, we're going to see this regular pattern start to emerge. So let's go back now. Okay, so again, as I mentioned in the previous slide, it turns out that in the population, approximately 50% of the candies should be orange. So this is what the makers of Reese's Pieces say. They say that 50% of the candies that they create are orange. And as I really hope that you noticed when we were playing with that applet just a little while ago, where we were taking candies out of that big candy machine, I was hoping you were paying attention to the pattern that was starting to emerge when we took each sample proportion and we graphed that. We kept doing that over and over again. Over time, we noticed that a regular pattern started to emerge. The pattern, so if we kept going and took lots and lots of samples, thousands of them, we would see something like what you see below here. And what are you noticing about this pattern? I'm hoping that you're noticing that it has a normal distribution. So in certain circumstances, we can expect, if we take lots and lots of samples and look at the collection of sample statistics, that that collection will have a distribution that's normal. And soon we'll talk about when that's going to happen, under what circumstances you can expect to see that normal distribution. For now, we just want you to notice that this is a distribution you're familiar with. We studied this distribution very closely and carefully back in chapter 13. And we can now use what we know about the normal distribution to answer certain questions related to sample statistics. So that's what's really cool and neat about chapter 18, is that it relates back to chapter 13. We already have a lot of the tools that we need to answer questions. We're just going to do things now in a slightly different way. So again, more about this idea of a sampling distribution, and I know I've said this already. I'm going to keep saying it because it's super important. But remember that a sampling distribution of a statistic tells us what values the statistic can take in repeated samples from the same population and how often it takes those values. And this is, again, what I tried to focus on in the last slide. So we have all these different values of the sample statistic. Under certain circumstances, we can describe the collection of sample statistics based on what we know about normal distribution. So that collection of sample statistics will be normal in shape under certain circumstances. And when it is normal, or when we can be confident that it's normal, we can apply what we know about normal distributions. So we can apply, for instance, the empirical rule. We can convert values to z-scores, and then we can use table B. So we're going to do a lot of what we've already been doing, only now, rather than working with one individual value, we're working with a sample statistic. So I wanted to make sure that I let you know this is very important, so pay attention. So I think one thing that's important to note here is that we're talking a lot about, what if we could repeatedly sample, and what would all the different sample statistics look like? In the real world, if you're conducting a study, you generally just take one sample. So you don't repeatedly go and take lots and lots of samples. So you have just one shot to get one sample, but to really say something about that sample, to make an inference back to the population based on that sample, you have to have an understanding of how your one sample compares to all the other possible samples you could have drawn just by chance. And so that's what an understanding of the sampling distribution helps us to think about. If we could have drawn other samples, what would things look like? How does our one sample compare to other samples that we could have drawn? And when you have this understanding of that, when you can think about that and visualize that, we hope it's going to be easier for you to see just why we can make an inference about a population based on just one sample. So think about this. Let it percolate. We'll come back to this, but this is a really important big idea. So let's look at some applications about this. Why do we care about this? What kind of questions can we answer based on this? So again, here's the question. What's the probability? Now keep in mind here, I'm asking for a probability. I want to see an answer in the form of a probability of observing 60% or more orange candies in a random sample of 50 Reese's Pieces. Okay. So again, to be able to answer this question, I need to understand what my sampling distribution would look like. If I took lots of samples and looked at all the statistics, what would I see? So to be able to answer that, or to get us started, there are three things I'm actually going to need to know about the sampling distribution. I'm going to need to know what the mean or the center is. I'm going to need to know what the standard deviation is, or the variability, and I'm going to need to know the shape. And it's really lucky for you that statisticians have already done a lot of this work for us. They have studied sampling distributions very, very carefully. And they know how things are going to turn out if you could take lots and lots of samples. And so because of this, you don't have to be taking lots and lots of samples. We already know what the characteristics of the sampling distribution are going to be. And so I'll show you and I'll tell you about that. And you'll see coming up when we get into chapter 21 that if you simply know something about the sample size and a little bit of something about the population, you can easily construct your own sampling distribution. You don't have to go through the process of simulating taking many, many samples. So here is here's a distribution we're going to work with in the next few examples. So if I took many, many samples of size 50 from the population of Reese's Candies, I get a distribution that looks like this. It has a particular mean or center. I'm hoping you can see this here. It's 0.5. So this middle is at 0.5. This distribution is centered at 0.5. It has a standard deviation of 0.071. And we can see that the shape is normal. So this is important, knowing the center, knowing the standard deviation, knowing the shape. These are three important characteristics of a distribution. You might remember we talked about that back in chapter 12 and chapter 11. So we're going to use this information now to answer some questions. So I'll pause here and then we'll come right back and work through some actual problems.